Alright, so there's one sort of nagging question that was left out of the last video, and something I always try to come back to at some point in Calc 1. And it's kind of an obvious question that perplexed me as a student. I mean, you see the proof of FTC 1 and 2 done carefully. If you look at my notes, it's all there. And again, I'd spend probably a solid week of class proving it in Calc 1. If you haven't done that as a math major, you really should stop and do that. Anyway, that said, you get to this formula and you're still left with just this kind of like feeling, this is a weird formula. Like, why does this area, right, which involves all the points from A to B, somehow just allow itself to be calculated by the difference of the antiderivative at the endpoints? It's mysterious. This formula is very mysterious. So let me just try to take some of the mystery out of it a little bit by just showing this little calculation. So here it is. Suppose f has an antiderivative big F, all right? And what I'm going to do is I'm going to apply the mean value theorem to the antiderivative on the subinterval xj minus 1 to xj, where I have in mind the partitioning that we talked about in the first video. Now, so if I apply the mean value theorem, I can pick an x sub j star in the open interval from xj minus 1 to xj, the jth subinterval, such that the derivative of the antiderivative, right, is equal to the average rate of change of the antiderivative on that subinterval. But the derivative of the antiderivative, of course, by definition, is little f. So that's little f of the x sub j star, the point whose existence is given to us by the mean value theorem. All right, all I know about that point is that it's in the subinterval, but that suffices, right? And I also know that that particular point is the one for which the value of little f, which is equal to the instantaneous rate of change of big F, is equal to the average rate of change of big F over that subinterval. So x sub j minus f of x sub j minus f of xj minus 1 over delta x. But of course, this is a lovely formula, but the one underlined in green is even better, because there we have the successive differences of xj and xj minus 1 as they go into f. Well, that's just equal to f of x sub j star, x upper j star, sub j upper star, times delta x. Well, that's very exciting, because this, remember, appears, that's essentially the jth term that we add up in the Riemann sum. All right, so there, let's just finish it. So we consider the nth Riemann sum using the x sub j star given to us by the mean value theorem applied to the antiderivative. And in so doing, I'm allowed to change this f of xj star delta x to the successive difference of f of xj and f of xj minus 1. This is what's called a telescoping sum, for the reason I'll show you just next. We'll look at these more in calculus too, but this is maybe your first exposure to it, I don't know. So like the first one, f of x1 minus f of x naught, that's coming from j equals to 1, 1 and 0. And then the next one goes to 2 and 1. The one that I haven't written, 3 and 2, 4 and 3, and so forth and so on, all the way up until n and n minus 1. And there's a successive cancellation here. It's kind of like, you can think about this being one of those old-timey telescopes that, well, I don't know, that I don't really watch pirate movies much, so I don't know. I mean, maybe there's been some pirate movie with one of these things in it recently. I don't know, whatever. Anyway, it telescopes down from many segments to just one segment, and all that's left, the only things that aren't canceled are this guy and that guy, right? So everything else cancels, and this is true for arbitrary n, so it's amazing. And also the partitioning is set up so that x sub n is exactly b and x sub naught is exactly a. So this actually just is the constant f of b minus f of a. Take the limit of both sides as n goes to infinity. Voila. The limit as n goes to infinity, the Riemann sum, which is by definition the definite integral from a to b, is equal to big F of b minus big F of a. So it's this wonderful cancellation, the successive cancellation paired with the mean value theorem is another way to look at why it only depends on a and b. I don't know if you find that any more convincing, but I personally find it reassuring. So anyway, so up next we should do more examples of u substitutions with bounds. I think I'm going to break the video here and start again